All right, ladies and gentlemen, I want to say a big welcome to all of you to the Valley of the Shadows of Management Science, specifically Time Series Forecasting. We have looked at several methods of time series forecasting. We've examined the moving average, the 3-period moving average, the 5-period moving average. And of course, you can do any of that also of the numbers. But there's a reason why we use the lower level moving averages, and we've explained that. We've seen how moving average can be done using Excel. We've also looked at the weighted moving average. All of these are ways to determine a forecast. So if you want to be able to forecast or generate a 3-month moving average forecast for the demand, you can calculate that. You take the 3 items before the actual divided by the 3, and then you get the number, and that number will represent the period under consideration. We've also looked at an exponential smoothing, a simple exponential smoothing, where the forecast is in such a way that you have an alpha with the demand, and then you have the 1 minus the alpha with the forecast. So let's say this is t plus 1, and you have t here. So we've also looked at that exponential. Then we looked at even adjusted exponential smoothing. So that one will require that you already have an alpha, then you also come and get a beta. And so that is taking into consideration a forecast before you use that forecast to do further forecasting. So we've looked at these, and today we want to go to something else, still within the forecasting environment, a new approach of forecasting, which is linear trend. Linear trend. Now, what is a linear trend? Well, basically, linear trend, what it's doing is you have time, and you know, demand is done over time. And sometimes over time, demand increases. Okay? If you take demand today, you look at your demand, it's not that much. But as people get to know about the thing that you are selling over time, people come in more. So demand increases over time. And when demand displays that kind of obvious trend over time, you can use an ordinary least squares regression. The regression line is sometimes called a linear trend line. You can use that to do the forecasting. And what it does is that it takes a dependent variable, which in our case is the demand. Remember, the dependent variable is the one being influenced. And then dependent variable is the one doing the influence. So the causal factor is the independent variable. And the recipient factor is the dependent variable. So when you look at the behavior of time, that can affect the behavior of the demand. So in this case, time is influencing or is causing demand to behave the way it is behaving. And you can use a linear model to establish the relationship, association, the relationship. Next semester, you will look more at the causality and correlation and different kinds of correlation and all of that. So how is the model like? Now, by the way, when I say a model is just a representation of reality. Okay. For example, if you take a selfie and you then, you took one picture of yourself, that thing in there is a model of you. Why? Because that thing there is a representation of you, the reality. So take this definition. A model is just a representation of reality. If you can manipulate the model, it can help you to manipulate the reality. So when you have a model of an aeroplane, you can now increase something in the avionics. And the way it will behave will give you an idea that the real one might behave that way. So this is a model. And in this model, I can rewrite it like this. I can rewrite the y as demand. Okay, I can rewrite the y as demand like this. Then I'll do equal to a plus time, where the time here is x. So now I have been very specific. Of course, there are other things that might be involved, which is the stochastic noises. We call it the error term. But for this purpose, we don't want to go too deep into that. But that is purely econometric. But then, if you take that out of the picture, this is a linear trend. A linear trend is basically like the equation of a line. You remember the equation of a line, y equals to mx plus c. Okay. And then we used to say that the m is a gradient or the slope, and the c is the intercept. And then the goal is that you know the values of y and x. And so now you should be able to generate c and m out of it. So this is basically a linear trend. Now, how many points do you need to generate a line? 2 points. So if you have 1 point here, you have 1 point here, you can create a line. And that is the essence of an equation of a line. So this is a linear trend. Now, what are the elements? A is an intercept, I've said it. And since A is representing time, A will start the time or the period at period 0. B is the slope of the line, X is the time period, and the forecast for the X is the Y. Okay. So if you want to forecast demand, then for period X, where time X, where the time X can be 0, period X can be 0, period X can be 1, period X can be 2, period X can be 3, and on and on. So for each time period, you know the demand, which is the forecast for the demand. This is an equation. This is a model. This is a model. It actually becomes a proper equation when you have the numbers populated. So using OLS, ordinary least squares, you can find the B, and after finding the B, you can find the A, or the other way around. Okay. Now, the process of finding the B from here is simple, but I don't want to take you through that mambo jumbos. But if you do the mambo in my econometric class with a master's and PhD, I teach some of these things. But just note that by some minimization and manipulation, you can get the B value to be this. This is a formula for the B, where the X is the actual period that you have. The Y, again, is the forecast for the demand. The N is the sample size. The X bar is the mean of the X. The Y bar is the mean of the Y. Then they are squares as well. Once you have the B, you can substitute the B into the X and Y. Remember, the Y bar is the mean of Y. So it means that Y bar basically is the sum of Y over N, which is what you have here. And the X bar is basically the sum of X over N. It's basically the average. Okay. And N is the sample size, which in this case is a time period, okay, which will start occasionally from 0. So this is what we mean by a linear trend line. Let's use this to fit a model. Okay. So this is a typical example of a linear trend. You have the period, which is X. And I'm giving you this data actually. Okay. So these are the period is 1, period 2, period 3, up to period 12. Now we don't have period 13. And so we can use some principles here to predict period 13. Now I use the word period, which means that the period can be 12 years, it can be 12 months, it can be 12 days, it can be 12 hours. So it's just a period. It can be any particular period. It doesn't mean that it's 12 months. For each of the period, the demand for computer services is here. 37 computers are demanded, 40 computers are demanded, 41 computers are demanded, and all of that. We have this data already, all the way up through. In a linear trend line, all you do is to find the xy and the x squared. Why? Well, look at the formula. The formula requires that we know the x, we know the y, find the xy, which is multiplication of the x and the y, and then find the x squared. That's all. And you substitute to get the b. Okay, so to find the xy, just take x here, multiply by the y. That gives you the first one to be 57. Okay. The second one, 2 times 40. That gives you 80. The third one, 3 times 41. And that gives you 123. And on and on and on and on. You can get that. And you can have the summation of each one of them. What about the s squared? If you take 1 and you square 1, that gives you 1. If you take 2 and you square 2, okay, that gives you 4. If you take 3, okay, that's 1, that's 2, that's 3. If you take 3, you get 9. And if you take 4, you get 16, and on and on and on and on. So that's how you find these. Now, according to the formula, once you get this, you can do the rest because it's a matter of just substituting them into the equation. How do you do that? Well, look at this. So if you look at that, we can find the mean of x. I've added the x together. If you add all of them together, you get 78. You will do this in an exam condition, so please, it's nice you know manually what I'm saying. If you don't understand, you ask right now here, I'll support you, I'll guide you, I will open your mental gymnastics. If you look at the y, if you sum all of them together, you get 557. Okay, 557. And then if you look at the xy, if you sum all of them, you get 3,867. And then the x squared, you get 650. So with that knowledge in mind, we can get all the things that we need to get. To get x bar is just the sum of the x, which is the 78 by 12. The 12 is a sample, the period. And then the y bar is also 46.42, as you can see right here. What about the b? Well, there's a formula, and this is the summation of xy, which is the 3,865. So that's the summation of xy. This is it. So that should replace the one here. What about the n? The n is 12. So that is going to be there. What about the x bar? X bar is 6.5. It's multiplying y bar. Y bar is 46.42. What about the x squared, the sum of it? S squared, the sum of it is 650 here. What about the n? The n is 12. We've said that already. What about the x bar squared? The x bar is 6.5. So we are looking at 6.5 squared. That's what is going to be here. So you do the substitution for each one of them. Normally, I would ask you to do it and tell me your answer. But if you do it correctly, and I know you will do it correctly and verify it yourself, because under exam condition, you should be able to know how to calculate all of this. Once you do that, and you always get a question on this, take note. So once you do that, that will give you, substitute them, 3,000, blah, blah, blah. Remember, I told you that the 6.5 is squared. That's it. If you do all of these mumbo jumbos, you're going to get 1.72. That's a B. Okay. Now, how do you get an A? To get an A, you substitute this. Now, what is that? Well, you know that y bar is already known. Y bar is 46.42. Okay, minus B. B is what you just found, which is 1.72. Multiplied by x bar. X bar is 6.5. Okay, so you substitute that, and if you do that correctly, you will get the value of A to be equal to 35.2. Ladies and gentlemen, now that you've gotten this, you need to write the equation all over again. Okay, remember, the equation is supposed to be y equals to A plus bx. Now, if the b is minus, if any of them is minus, you indicate. Now, what is the value of A? It's 35.2. So you're going to have y equals to 35.2. What about b? We find the b to be 1.72. So you do plus 1.72x. And that becomes your equation. Okay. You should be writing some of these things down. Write it down, because the more you write, there's just an information symmetry between your fingers and your brain. Okay, so this is equation actually. Beautiful equation. Now that we have this equation, we can use it to predict for period 13. Okay, so it's like now having the value for X. We don't know period 13. Suppose you have this period 13. Remember, you just have to replace this one, continue from 11, 12, and 13. So if it is 13, the question is what would be the value of Y? That's what we are looking for. If you look at the trend carefully, you can see that they are all increasing a bit. Now, if we get 13, what is the value going to be? That is the next thing we want to predict. So this is the forecasting part. Well, in order to get the demand for period 13, substitute the 13 into this X here, because that is the period, and then solve for the Y. If you do that, and I know you do that correctly, if you do that correctly, you are going to get this value, 57.56. And ladies and gentlemen, when you carefully check it, you will notice clearly that this is in line with what we have here. Because if you look at this, we had 52, 55, 54. Now we are getting 57 for the period 13, which makes sense. It's within those parameters. So based on the linear trend line, we are able to predict for period 13. The question, however, is whether this prediction is correct, whether it is good, whether it is correct. That will be another thing we'll look at later. So at this stage, if you have a question, please let me know. Let me know if something wasn't clear. Okay, let me know so that I can address it right now, so you know that I'm not going to struggle with this ever again. Ever again. Any question? Fantastic. So now let's proceed. Now that we've been able to calculate this Y value, okay, predictive value for Y, we can now go ahead and draw it. Of course, you can draw it. The actual value, if you plot it, is going to be those zigzag. The linear trend line is a straight line, as you can see right here. Okay. And actually, the data is also in Excel. So we can go to Excel and see the trend there, actually. Let me see if I can do that quickly. I didn't put that here. So this is the data. Okay. This is the X here. Okay. Let me highlight it with a highlight of, let's say, orange. And this is the Y. Let me highlight it with a highlight of orange. Okay. So now what we are going to do is I'm going to select just X and Y here. Okay. And then on the insert at the top, I'm going to choose scatter under the chart, scatter. You click on scatter, choose the first one. Okay. And this is a scatter. Now I want to give the name. Okay. I want to give the name of this. So go to quick layout on the far left and select this one. Any one of them, actually. Okay. Any one of them, you selected that. But I want to just use it. You can also use, in fact, this one will give you everything that you need, to be honest with you. Because it's giving something that I'm looking for. So this one. Now, at this stage, you have to name it yourself. Remember the Y-axis is the demand. Okay, so here you need to rename it and call it demand. So I'm just going to type it myself and call it demand. The X-axis is a period. So I'm going to type it and call it period. All of these legends are not necessary, so you can delete the legend. Okay. And the title, which is a demand, is not necessary, so you can delete the title. And now, this is it. It's not too clear because of the grid lines, so you can just go to the top here and select one where there are not many grid lines, like this, or like that, or like this, whichever one that is good. I think I'll take this one. Okay. Now, you can move also this equation down as I'm doing. You can even bold it by doing Control B to bold it. And you can see that this is actually the equation, isn't it? the 1.7238, and then the 35.21. That is very, very, very similar to the one we had. Let me just show you the one we had. Okay, 1.72, and then you have 37.2. Okay, that's exactly what we have here. So what is this showing? As you can see, it shows a clear positive relationship between the demand for your product and the time, as the time increases. So as time increases, you can see that there's an increasing trend. Okay, there's an increasing trend. And you can see that right here. This is why it is known as a linear trend. And based on this, of course, you can do your prediction. The prediction is done by substituting it into the equation. The R-squared value here, you will learn this in next semester. The R-squared value here is called the coefficient of determination. It tells you by the proportion of explanation that the independent variable provides for the dependent variable. Okay, so the fact that it's 80% on average here means that 80% of the variability within the demand has been explained by the time period. So that the period explains 80% of the variability in the demand. That's what it means. And of course, there are several statistical analyses that you got to do. So it's not just looking at a thing, but it's also making sense of what you're looking at. So this is a graph. This is the movement. Okay. So that's time trend. And the goal was to use it for prediction. It's not just to come and generate anything. It's basically to use it for prediction. Okay. Now, so next thing to do is, so you can see that our linear trend that we wrote, the one we drew. Okay, you can see that it's similar to this one. You can see that they also labeled it as demand here and as period there. This is basically, I don't have any more assignment to give you. I would have given you an assignment to do that. You can see that here you still have the demand here. Okay, and then on the bottom you also have the period. Okay, and the linear trend is that these ones are things you have to draw yourself for the actual one. Okay, for the actual one, you can just click on each one like this, and then you can put a quick line trend. What do you call it? Let me see. You can put some quick line formatting right in there for it, and that will make it cool. Eh? So this is a linear trend. This is exponential. This is a forecast, linear forecast. This is a moving average. So you can see I've just superimposed the moving average on it. And you can see that the moving average is showing some couple of. But there are more time trends if you want. There are more time trends here that you can actually, you can even customize your own time trend. Anyway, but the key point is we have been able to generate a linear equation. Now, let's move on. The next method, so we've been able to use a linear trend line to do forecasting, to forecast for period 13. The next one is we're going to look at a completely different thing, which is known as seasonal adjustment. Okay. Now, let me just remind you of some few things that we did last week or last time before your enjoyable period. We looked at exponential smoothing method and then adjusted exponential. Those things are methods for forecasting. But what we're about to look at now is seasonality. So you're going to look at a situation where you bring season into the thing because certain things change season. Okay? It is a season that might cause demand to change. A seasonal pattern is a repetitive up and down movement in demand. Repetitive. So subsequent period, it will continue. But there's a repetitive up and down movement, like that. Now, the patterns can occur daily, weekly, monthly. I've said this already. They can occur daily. For example, we know that every day at around a particular time, there's a kind of a breakfast that people are eating or lunch that people are eating. Or there's a particular time the sun is on. Sometimes every week you also know that there is something like you have a lecture all the time, every week at a particular time. So these are patterns. Now, you can have a seasonally adjusted forecast. You can have that. So you can have the seasonal demand, and then you can have the adjusted version of the seasonal demand to forecast what is going to happen. And you can get that value by multiplying the normal forecast by the seasonal factor. But the question is that you're going to ask the question, what is a normal forecast and what is a seasonal factor? Okay, ladies and gentlemen, a seasonal factor is when you divide the actual demand for each season. So how many seasons do we have? How many kind of quarters do we have? We have 4, right? We have 4. So let's take each one as a season. So you take each season, you divide it by the total annual demand. Okay. How many months are in the year? There are 12 months in the year. Okay. How many quarters are in the year? Who can tell me? How many quarters are in the year? Come on. Type it there. Say 4 quarters, exactly. Okay. So now, with that number in mind, you're going to have those 4 different quarters. So, quarter one. I think we have an echo from someone. Yeah, these are people who normally don't pay attention in class, and I know. All right, so quarter one, you're going to have. So first thing we're going to do is to find our annual demand. So we're going to take an example data. And you might get a data set like this in an exam as well. So how do you calculate the seasonal factor? Guys, write this formula down. Write this formula down, because if you write it down, it helps you with what I'm about to tell you. Sometimes you watch and watch, you don't write, and it's not good. It's not a good practice of learning. All right, so S here is a seasonal factor for each particular demand. D is the actual demand. And the sum of D is a total demand. As the name sounds, is a sum of D. So all the individual, quarterly demands, sum of D. So we're going to calculate SI for each quarter, okay? For each season, you might say. We're going to calculate that. And for each season, we need to take the DI divided by the sum of the demand. Let's take a practical example. Okay. So we are going to calculate the seasonal adjustment. And I've already said this, or maybe I haven't, but the seasonal factors, the SI, they lie between 0 and 1. Now, who can tell me why am I saying that the values of the seasonal factors lie between 0 and 1? Who can quickly guess? Who can quickly guess why? Okay, they lie between 0 and 1. I know you're in the class, so you don't want to talk. Okay, but the reason why they lie between 0 and 1 is because each quarter is a microcosm of the whole year. Each season is a microcosm of the whole year. So if you have 4 quarters, it means that the total quarter is 4/4, isn't it? And so one of the quarters is 1/4. Another quarter is 1/4. Another quarter is 1/4, like that. And then you have 4/4, which is 1. So the maximum value is 1. Okay. Now, the seasonal factor tells you the percentage of the total demand assigned to each season. Or in other words, what is the contribution of each season towards the total demand? So for example, suppose you go and do brilliant science and math quiz. You select some people. And when you select those people, if those people go and then they lose, we don't say those very 3 guys have lost. We say that the school has lost, because they are just a representation of the whole. Okay. So seasonal factor is telling you that percentage contribution of that season towards total demand. And some seasons can bring a lot of things. And when you get as a manager that a season is bringing a lot of things, you pay attention to that very season. So Christmas season, Easter season, Valentine's season. Some people are plotted this in their calendar so much so well that it doesn't matter. They are going to make it. Whilst people are sleeping and all of that, they are raking income because they know those are the periods of time. That's what I do as well. In my business, I make more income on December and April, March and April, and multiple places than on the usual side. Whilst others are having time, the season has been calculated ahead of time. So we're going to take an example of a wishbone farm. It's a company that raises turkeys. They raise turkeys. Turkeys are better than chickens anyway. And they sell it to meat processing company. But during the peak season, obviously the peak season happens during the fourth quarter of the year, October to December. That is when they get a peak. That's when there's a lot of demand because Christmas time is coming. Now, Wishbone Farms has experienced a demand for turkeys for the past 3 years. So I'm going to show you the 3-year data, and the data is also split according to each season. So if you look at this data, in the first quarter of the year, okay, this one, in the first quarter of the year one, the demand was 12,600. Okay. The second quarter for that same year, it was 8,600. The third quarter was 6,300. The fourth quarter was that. The total amount was 45,000. Okay. For year three, the same thing. The first quarter was 15,300. The second quarter was 10,600. The last quarter was 19,000. And you can see that all of them, the last quarter is generating lots of demand. Okay. So now, when you now get the total of that and you now add all of these totals together, you are going to get 148. This is what we call the annual total demand. Okay, good. Now, the question is, how do we calculate the seasonal factor? You remember that we did say that the seasonal factor, the seasonal factor, which is a S, is you take the demand for each quarter, that's the total demand for each quarter, which are here. These are the total demand for each quarter. Then you divide it by the overall demand for the year. The overall demand for the year. So who can tell me how the first one will look like? If you want to calculate the seasonal factor for season one, so if you want to calculate S1, it will be what divided by what? This one I need an answer. It will be what divided by what? Yes, let me see what some of you are writing. I need an answer, please. This will give me a clue whether I'm really here with you guys. If it's still giving me a clue that I'm not here with you guys, I'll fly, because then it means that you are not that ready, so I can fly, move faster. Okay, and then you can watch it later. Maybe that's your goal. I should be able to give me an answer. I'm not getting many right people giving me any answer. Okay, so when you do that, you're going to get 42 divided by 148, and that is going to give you seasonal factor 1. Okay, and you can do the same thing for the others. So for the first one, you're going to get S1, you're going to get 42.0 divided by 148.7. That will going to give you 0.28. That is a seasonal factor for season 1. Okay. And this is talking a lot. He's talking without raising the hand. Marilyn, are you with us? Let me mute all of you. All right. So that is it for S1. Okay. If you calculate it for S2, you're going to get 0.20. Okay. If you take its 29 by the 148, S3, S4, you can calculate the seasonal factors for that. You always get an exam on this. Okay, it's similar to this. Okay. The next thing now is, so you got the seasonal factors. And that seasonal factor is nothing. You see, our goal is to find the annual demand forecast. What we have here is seasonal factor, but we need the annual demand forecast, the yearly forecast. What is it going to be? To do that, First, we need to multiply the demand forecast for the year. We don't have the demand forecast for the year by each of the seasonal factors, and we have each of the seasonal factors. Okay? But I need to have my demand forecast for the year. Then I multiply each of, sorry, the demand forecast for the year is one value. Okay. And I will use that one, but let's say I get that value to be 80. I'll multiply the 0.28 by 30, 80, 0.20 by 80, 0.15 by 80, 0.37, each one of them by 80. Okay. And that is what I'll need. That will help me to get the forecast demand or the demand forecast for each quarter. The demand forecast for each quarter. So what did we find? What we found wasn't demand forecast though. Look at it. What we found right now was 0.28. 0.28 is not demand forecast, it's seasonal factors. The seasonal factor. But demand forecast will mean that we have the forecast for each of these demand, each of these values. So 12.6, what is its demand forecast? Okay. 14.1, what is it? So for each one of them, we should be able to have the demand forecast for each quarter. Each quarter. So when you take each year, the quarter value you need to get. How do you do that? Well, one way you can do that is to get the demand forecast, is to get a yearly forecast. I've said it. If you want to get the demand forecast for the quarter or quarterly demand forecast, you should get the yearly demand forecast, basically. Okay. Now, when you look at a trend, look at it carefully, look at a trend, you will see that for each year, as the quarters are increasing, the values, the demand is also increasing. So if you take the first year, as we are getting to the end of the year, demand is increasing. And also when you take the year by year, from year one, is increasing downward. That's the most important one. So from year one to year two to year three, demand is increasing in each quarter. Year one to year two to year three, demand is increasing. And then for year 4 to demand is increasing. So demand has an increasing trend over time. Watch that word, over time. What does that remind you? Which method can you then use to find the yearly forecast? Because demand is increasing over time. So we can use a linear trend, isn't it? Okay. We can use a linear trend. Okay. So we have to compute a linear trend for the 3 years because demand is increasing over time. Whether it's increasing over time or decreasing over time, there's still a trend. That's the point. So we got to use, that reminds me. So what demand? Then you have to remember your y equals to a plus bx. That same one we just finished with. Okay. So how do you do that? But to do that, watch it. To do that, you have the totals, don't you? Okay. You're talking about quarterly. So for each quarter here, you have 42. But then now we are talking about the year, so you have to calculate the year. So you're not going to use the quarterly one again. You're going to use the year here to represent what? The demand. To represent what? The demand. So when you go to yearly, because you are looking for the yearly, when you go to the yearly, the period will be X, and then the demand will be Y. As for the periods, you know them. The X's are the time, because you are using time trend. So you have 1, 2, 3. They are just 3 years. And what about the Y? Remember, this is yearly. The yearly one is going to be 45, and then 50.1, and then 53. Blah, 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 blah. So you have it for each one of them. So now you have your X, you have your Y, you can find your X square, you can find your XY, you can quickly find your linear trend line. Cool, isn't it? Let me show you. So this is it. Okay. So you have your X here, you have your Y there. You can multiply the X by the Y to get each one of them. Then you can take each Y and each X and square it, and that will give you this one. Then you sum them because you're going to use the sum in finding your B. The B we just found. In case you've forgotten about it. Okay. So you sum them. This one will give you 6. Now you have to find the mean. If you can remember, the formula requires you to find the mean. So you take the 6 divided by the 3, the mean is 2 for the period. What about demand? The total is 148.7. Divide that by 3, and that gives you the mean of 49.57. Okay. What is the next thing? The next is to find the B, the formula. This B. Okay. And now the B requires you to find sigma XY. And what is a sigma XY? It's down here. Okay, it's 306. You substitute that 306 here. And just look push it. So this, you calculated the sum of all of them. I would normally say that calculate the sum of all of them and always calculate the mean also of all of them because you're going to use them. Then you substitute this. N is a sample size, which is a number of periods. There are 3 periods. Okay, and then you have the sum of the period, the X bar. The X bar is 2. You got it from here. The Y bar is 49.57. You got it from there. You substitute that. The summation of this one is 14. You put it there. And then the rest is just easy peasy. When you do that, you're going to get the B value to be 4.3. Once you get a B value, I'm sure you can get to the A. Okay. You remember that the A is just taking the mean of the Y minus the B, multiplying the mean of the X. The mean of the Y are all here, 49 point blah, 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 minus the 4.3. You substitute, you get the A to be 40.97. So now that you got this value for the A and you got this value for the, in fact, you can just take this data set, this small data set, and put it into Excel, and it can generate the same equation. But let's write the equation of the line. The equation of the line is this, and this is the same as the linear trend line. So now, using this, we can predict for year 4, can't we? Because we have for year 3. You see, we have 1, 2, 3. So if I want year 4, what do you think I have to do? We have year 1, we have year 2, we have year 3. If I want year 4, or sorry, period 4, you just come and substitute it into this X. Because remember, the X's are the period. So you put 4 there, multiply the 4 by the 4.3. Whatever answer you get, you add it to this 40, and that will give you the demand forecast for year 4. Not for the quarter 4, but for the year 4. You will get this in an exam. Take it. So once you get this value, oh, by the way, the value is equal to this. Let me just show you the value. So when you do that, you're going to get this value, 58.15. That is for the year 4. What do you think now we need to do to this value to get the quarterly demand forecast? Okay, that was the whole idea. Now we need to find the quarterly demand forecast. What do we do now with this 58.17? What do we do? Type it or raise your hand is one of them. Okay, good. So we go and put this one right into multiplied by the seasonal factor. You see, you remember the seasonal factors are here. Okay, seasonal factors are here. And we said that if you want to get the quarterly demand or the seasonal demand forecast, okay, you just have to multiply the seasonal factors. It's here. Okay. What was that statement? It's here. Multiply the yearly forecast, which is this statement here, by the seasonal factors to get the quarterly forecast demand. That's it. This 10 sentence. So if you, it's basically like this. If I want the quarterly should be equal to the yearly demand forecast, okay, the demand forecast for the annual period, multiplied by the seasonal factor. Okay. And that will give me the quarterly factor, sorry, the quarterly demand. So if I want to say this is for each quarter, let's say quarter, okay, then D for the annual multiplied by the seasonal factor, and that should give me this. So we can get that for each of the quarters by multiplying the 58, whatever that we found. Okay. We're going to multiply this 58 by each of the seasonal factors. So that's it here. So using the annual forecast of demand, the annual one, we can now find the seasonally adjusted forecast, or what we call the seasonal forecast or seasonally adjusted forecast, SF. The reason why we have to do seasonally adjusted forecast, SFI, so that it will not confuse with the seasonal factor, which is also SI. Okay. So using that for year four, because now all of them don't have year four. So if I want to get, let me show you something, guys, if you are following this. So you see for year, we are looking for year four here. What is that? Year four, we are looking for the value for this quarter, value for this quarter, value for this quarter, value for this quarter, for year four. That's all we are looking for, okay, for each one of them. And that is what we are trying to just use everything we've done here to find that. Just want to delete this. Okay. So how do you do that? You take each one, multiply it by that. You take each one, multiply it by that. So we're going to calculate for year four for the first quarter. Okay. So this is SF1 for quarter one. We take the 58, we multiply it by the seasonal factor. We got that. Quarter two, we take the same 58, which is the yearly forecast or the annual forecast of demand. We multiply it by the seasonal factor. We take the same 58, multiply it by the seasonal factor. We take this one, multiply it by the seasonal factor, and watch it carefully. You can see that again is also following that same increasing trend. And you can see that the forecast for quarter four is also the highest among all the quarters. Okay. So that is it. Let's compare this with the actual demand. Okay. And you will see that the forecast is very good. Where is the actual demand? Let's show you. There you go. So if you take actual demand like this, like let's say for year three, okay, you have 15.3 and the last one is 19.6. You can see that the forecast we have is 21 point something, so it's bigger than all of them. Look at this one. Okay, it's 15. I'm taking the third one because the third one seems to be the best. So if you look at it, it's 15.3, that's quarter one, and then 19.6, that's for quarter four. Okay, so let's look at our quarter one and quarter four. Look at it. Quarter one here is 16.28, quarter four is 21.53. So comparing that with the actual demand, these are good. First of all, it shows seasonality. Second, it also shows upward trend. Upward trend because from 16, it came down though, but then there's still eventually there's a huge upward trend. So you can see that it's a good forecast. This is it. You always find this thing. Now that you have finished the forecast, we need to know whether the values we have are correct. Now, we are not going to use even this data we used. We are going to just remember our first data set that we had. What shows that our forecast is correct? But now we looked at several approaches, haven't you seen? Okay, we've looked at moving average. We've looked at weighted moving average. We've looked at simple exponential smoothing. We've looked at adjusted exponential smoothing. We've looked at linear trend, and now we've looked at seasonally adjusted forecasts. Look at all this. How do you know which one is the correct one? Well, there's something we use which is known as forecast accuracy. Forecast accuracy will tell you how the actual values deviate from the forecast value. And when the value is small, when the error is small, so we are looking at the difference between the forecast and then the actual, okay? And if the difference between, so let's say that the forecast is 4, the actual is 2. So you have 4 minus 2, you have 2 for one of the forecasting errors. So the error is 2. You go and calculate another one, the other error is 1. You calculate another one, the error is 4. Then in this case, you're going to choose the one with the smallest error. That method is the best. That method is the best. And there are several forecasts. We're just going to look at 4 of them. Okay. Mean absolute deviation, that is common. Mean absolute percentage deviation, mean squared error, root mean squared error. They are all similar, to be honest with you. And I'm going to take one of them. Okay. So let's look at the mean absolute deviation. How you calculate it is the most important thing. So that one, you have your demand, the actual demand minus the forecast. Then you take the absolute value. Okay. Once you take the absolute value for each one of them, then you sum them and divide it by the sample period. That's it. I'm going to take my Excel here and then show you with an example that we did. I'm going to move this one to the right-hand side here. I hope you guys can see. Okay, so look at our data set. This is our data set. Okay. Forget about January here. I'm going back to the old data set. Okay. Remember, we used to have this old data set that we dealt with. So this is the old data set. So in this data set, we have some periods here, period 1 to 12. And then we have some demands here. Okay. And we were able to calculate the moving average, if you can remember. We also calculated the weighted moving average, the exponential moving average. Okay. I'm going to show you some things. Okay. So I'm going to show you how to calculate the mean absolute deviation. Let's take the same data I have here is what you are seeing here. So we decided to calculate the simple exponential smoothing. If you can remember, I know some of you may have forgotten, so let me just remind you how we calculated it. Simple exponential smoothing. Do you remember this formula at the bottom? Where we said that the forecast for the next period is alpha, which is a smoothing factor, multiplying the current period plus 1 minus the alpha, which is a dampening factor, then times the forecast for the current period. So we want the next period. So we need the current period demand and then the current period forecast. And for this, look here, the demand, the current period demand is 37. 37. Current period forecast will also be 37. And that is what is here, is 37 here. Okay, so that's this one. Okay, yeah. We've done this already. Now, for period 2, you need the current demand, which is 37 here. Okay, so that's a 37 here. Then you need, so I'm doing for period 2, okay? I'm doing for why we got this 37. Then you need the current forecast. The current forecast is also 37. So I substitute the 37 here, 37 here. And then you find the answer and you get 37. So you can see that the forecast for period 2 is also 37. Now, how did we get period 3? You will change this one to 3. The 2, you change it to 3. Then you use D2. D2 is what? Is 40. So you substitute 40 here. Then the forecast for period 1, this one will be F2, which is 37. So you have 37 here. So you have 0.3 multiplying 40, then 0.7 multiplying 37. If you check it, you will get 39, 7.9. So that is how we got the forecast here. We did this the last time. How do you find the error? Well, take the demand minus the forecast. Demand minus the forecast. Demand minus the forecast. Demand minus the forecast. Each one, okay? And that will give you the error for each period. Then you want the absolute value. So all the minuses will go. So this becomes the absolute value. And then once you get the absolute value, in fact, in Excel, you can do this and add the absolute value straight away for it to give you the result. If you do all of that, you sum them, and that gives you, that is a sum of the absolute value. Guys, let me show you something. This is what the formula was saying. Look at the formula. The formula said that after you've gotten the difference, the error difference, the difference, then you take the absolute value, then you sum them, then you divide it by n. That's it. So let's go to our Excel here. I've done it in Excel, which I've sent to you, and I've also done it manually. Oh, we have to know that we are using this period 3. The K value of 3. So we are using this K value of 3. So this column here, that's a column we are using. So we sum them, we get this value, which is 53, as you can see, we get 53.386. Okay, that's the value you get when you sum all of them. And I've also taken the absolute value. So if you look here, you see there's an Excel symbol called absolute value. So if you double click, you see that it has ABS. ABS stands for absolute value of the number. So this gives you the absolute value straight away. And then you sum all of them, you get 53. Now, how do you get the minimum absolute deviation, the final one? Sorry, the mean absolute deviation. To get a mean absolute deviation, go to the formula. The formula says that you take the sum you had, which in our case is 53, divided by n. What is n? Okay. We know the value of n. N is actually supposed to be 12, but then there is no error for the first one, as you can see. Okay. So we always cut it short by the number of error values that we don't have. Okay. Just so that, because you can see that the first one, it was 0. It was not available actually, because there's no error. So we actually have a kind of a sample of 11 periods instead of 12 periods. And that is how come we get 53.41, which is the sum here divided by the 11, that's 4.85. So the mean absolute deviation is 4.85. So it. But we need to check against the other ones. Oh, by the way, when you look at this, there are some few things you take note. The lower the value, the better. I've said this already. Always, the lower the error, the better. The more accurate the forecast is. So at that forecast we had, what was the forecast? Let me just go back to the Excel and show you. Okay. If you go and check the forecast we had for this 3, look at it. Okay. The forecast we had was 51. We had 51 here. Let me blue it. This 51, which was for period January, period 13, this error, whether we believe it or not, we believe in it or not, will be determined by the mean absolute deviation. And the mean absolute deviation, okay, is a clearly showing 4.8 error. So it means that, well, maybe it's small, maybe it's high, but we need to juxtapose that against the others. So let's look at the next error computation. So you can see that the next one is, we need to calculate with the other method, because this method that we did a method for exponential smoothing. So we need to do for adjusted exponential smoothing, okay? And then we do it for the linear trend and all of that. I cannot go through all of them, but I'm going to show you some of them. So this is the mean absolute deviation. So we can use the mean absolute deviation to compare different forecasting techniques, which is what I'm about to do. So I am doing for the alpha equals to 0.5. So you see, the one I just did was alpha equals to 0.3. I'm going to do alpha equals to 0.5. And I've done it already. And again, you use the same approach. So instead of going through this thing, okay, let me show you. Instead of going through this thing and making this 0.3 for the alpha, no, you're not using 0.3 for the alpha. You're going to just use 0.5 for the alpha. And everything else remain the same. If you should do that, which I have done here, watch it. I've done it in this column here. Just delete this so that you can see it well. So there you go here. I've done it in this column here. And you can see that in this column, okay, when I added everything, I even did it here properly using the absolute value. Okay. So when I did everything using the absolute value, you get this number. And now you divide this number by 11 again. And remember the first one, when it was 0.3, you got this. When you divide it by 11, you get 4.0. So as you change the alpha upward, you can see that the error comes down. The error comes down. So I have calculated this for exponential smoothing using 0.5. Okay, using 0.5. I'm going to do the same thing for the linear trend. But this time, I can use 0.3 or 0.5. Okay, so watch what I did here. Let me just delete this one. So using 0.5, okay, I calculated this, I got 4.04, as you can see. In fact, actually, somebody says, why didn't you divide by 12? It's a good question. I said it here, okay? Because when you look at this one here, for period 1, there was no error. Watch it. There was no error. So you cannot consider that as necessary, okay? There was no error. Period 1 is on a period where you did not find error. And all you are doing here is that you are calculating errors. So because there was no, and remember, you are looking for the absolute value. And because you are looking for the absolute value, okay, there was no error. The absolute value of 0 is nothing. Okay, it's like you're moving everything to positivity. And if there's no error, or if the error is not there, then there's no error. I don't know if you get me. Like you're looking for an error, the error is not there, so there's no error. So why do you want to include that period as part of the error? That's why we didn't include it. Okay, I hope you understand. If you don't understand, just type it and let me know. Okay, so we did it for exponential smoothing for 0.5, and you get 4.04. And you can see that in the Excel here, the 4.04 is this, okay, for alpha equals to 0.5. Cool. What about the time trend? Okay. What about the time trend? Because remember, we did it also for time trend. Okay, so I did it for the adjusted exponential smoothing. And adjusted exponential smoothing, I use also alpha equals to 0. You know that one, you have the alpha and the beta. Okay. Alpha is 0.5, the same alpha here, and then the beta is 0.3. And when you calculate the mean absolute deviation, you're going to get 3.81. Guys, it's going to be the same approach. You can try that on your own. But I'm more interested in showing you how we did for the linear trend. The linear trend, when I did for the minimum absolute deviation, I got 2.29. Oh, how did I get that? Remember that one is giving you the lowest of errors, eh? So I decided to show you that one, how you calculate that. Okay. So let's go back here to the Excel. And by the way, you can calculate this manually. But I want you to pay attention here, because if you pay attention, it's going to help you on how to calculate. Remember, there are methods. We have exponential smoothing, simple one. We have adjusted exponential smoothing. That's not simple. Then we have linear trend. Those are the three that we are dealing with. We didn't look at the moving averages and all of those. We didn't bother ourselves with that. It's this one that we are interested in. And we've looked at the error associated with using the exponential smoothing, the simple one. The error associated with the adjusted exponential smoothing. Now we are going to look at the error associated with the time trend. Okay. Now, how do you calculate that one? Sorry, with a linear trend. With the linear trend, the formula is this. Is the absolute value of the D minus the F. Now, in case you have forgotten, the linear trend, okay, I need to give you the forecast for the linear trend. Is there. This is the forecast for the linear trend. Okay. I'm going to show you how it was calculated. Do you remember this formula? Let me just go back here. And I know some of you may have forgotten. That's why I'm going back here. Okay. Just remember the linear trend. Not this one, not this one, not this one, not this one. Okay. This one here. Okay. You remember this formula here? Okay. We were able to get this equation, and we were able to use that to even calculate for 13. All right. We're able to use this to calculate for 13. So we can use it to calculate the forecast for 1. How do you get the forecast for 1? Pay attention here. To get a forecast for 1, you're going to have Y equals to 35.2 plus 1.72 into bracket 1. And that will give you the forecast for 1. Okay. That will give you the forecast for 1. That's it. And when you do that, you're going to get 1. 1 times 1.72 is going to be 1.72. Add 1.72 to 37 point that, you're going to get something like 36.92, thereabout. I think so. 36.92. Let's go to the Excel. Yeah. Watch the Excel answer for that. There you go. Okay. Look at the highlighted blue here. Okay. Look at the highlighted here. And that is what? That is 36.92. So that is how I did it. So when I double click it, watch it. It shows the formula 35.2 is a linear trend equation. So use a linear trend equation. Of course, you will not be given this one in an exam because it's too many. Okay, it's too many. So maybe in an exam, the period will be just maybe 4 periods, 3 periods, 2 periods. Normally between 3 to 6 periods. That's it. But this one is too long. Okay. But that is use a linear trend equation. And wherever you see the X is standing for the 1, 2, 3 for the period. So that is what I did here. And then you get the forecast for each one of the period. Each one. Now that you've gotten the forecast, you're going to take this one, okay, and then you're going to take the actual demand, which is column C. You're going to take column C minus column H. So each demand minus this linear trend forecast. Each demand minus the trend forecast. Each demand minus the trend forecast. And then you take the absolute value. That's what I did in this column I. Okay. So if you look at column I, I'm taking column C minus H, the absolute value. Okay. Column I, I'm taking column C minus column H, the absolute value. Okay. And then once you're done with that, you sum them up. Okay. You sum all of them up. So that's what you see I've done here at the bottom. When you sum all of them up, you get this value. You sum all of them back, but you have to take the average. You remember the formula. The formula for the MAD. The MAD says sum them, take the average. Sum them, take the average. So when I double click on this, you can see that I am taking the average of the absolute value of the difference between the C minus the H. I'm repeating that. I am taking the average of the absolute value. And guys, the question is, why are we now dividing this one by 12? Who can tell me? Because the others, we didn't divide by 12, we divided by 11. Why are we dividing this one by 12? Who has been followed? Why are we dividing this by 12? Because there is a value at period 1. Excellent, Dinah. That's it. Because there's a value, and the value is 36.92. That is why we are dividing it. So when you do that, you are going to get 2.29. Okay. That is the absolute value, the average of the absolute value of the difference between the demand and then the forecast. So that's what we did, and that is what gave us this MAD value. Let me just go down. This is all forecast errors that we are calculating. We are calculating the forecast error for each one. So this is what gave us the forecast error of 2.29, okay, for the linear trend. Okay. So now on the basis of these three, if you are to ask which method is the best that you're going to use, what do you think is going to be the best method to use? Obviously, it's going to be the linear trend. And why? Because the linear trend is giving us the lowest error compared to the rest. So what is the conclusion here? That the linear trend has the lowest mean absolute deviation. It is increasing out. Even if you increase alpha from 0.3 to 0.5, okay, the improved smooth forecast version, the linear trend is still better. Okay. So that tells you that The linear trend approach is very it doesn't mean that it's always very good, but it means that it's very good for this purpose, for this very example. So that is one approach of calculating the forecast error and then using it to judge the accuracy of which method. MAD, mean absolute deviation. Let's look at the next one. I'll just look at just two of them. Okay. The rest are simple, but these two are key. The next one is the mean absolute percent deviation. As the name sounds, it's fairly simple. Mean absolute percent deviation. If you are to go back to each one of the methods, let's start with this one. So you look at the formula, by the way. It's the same thing as before. You take the demand minus the forecast. Let me just point it out here. This is a demand, this is a forecast. You take the difference and then find the absolute value. And then after you have found the absolute value, you sum these absolute values after you've taken the difference. You sum the absolute value and divide it by the absolute value of the demand. Now, where is the absolute value of the demand? When you go to the Excel, the demand is the column C here. You add all of them. You add all of them, that will give you the sum of the demand. So you divide it by the sum of the demand. I think I made a mistake by saying absolute value of the demand. I divide it by the sum of the demand. And when you sum this, then you get 520 here. When you sum all of them, you get 520. So you take this value here, the difference. So if I go to where alpha is 0.3, okay, you take that one, you find the difference, you sum that, you divide it by the 520. And I've done it for each one here. So let me show you. So I'm going to show you for when alpha is 0.3, this one. This is when alpha is 0.3. So you look down here. Look down here. When alpha is 0.3, this column here. This column here. Okay. You will see that first of all, I found the absolute value of the difference and I got 53. Okay. And that 53 is what I divided by 11 and I got this for the mean absolute deviation. But now I'm looking for the mean absolute percent deviation. And that's this. And how do you do that? It's very simple. Once you get this same one, so if you look at this formula, you get this same one, the same number that you divided by the 11, this time you divide it by the 520, which is the total demand. That's all. And when you do that, you get 0.103 or 0.102666. And you multiply that by 100, and that will give you the percentage. So in this case, you get a percentage value of 10.27. But that is for the 0.3. What if we are doing for the 0.5, when alpha is 0.5? You take the 40 and divide the 40 by the 420. And that will give you this, which is approximately down here, it is 8.54. So when I go to the results section, you see the first one is 53.41 divided by the 520. That gave us 10.3. That 10.3 was what we found here. Okay, 10.266, which is approximately 10.3. Okay. Now I have to do for when it is 5, then you do for the linear trend, then you do for all the blah, 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 blah. Okay, it is here. So this is when it is for 0.3. That's the one I've highlighted. When it is for 0.5, that's the one I've highlighted. So look at the values at the bottom. That's what we are interested in. So when it is 0.3, the error is 10.3%. When it is 0.5, the error comes down to 8.53. Okay. I did not do for the linear trend. Okay. Did I? I think I did. I think I did. It was last year. That's 5.3. Yeah, I think I did. But then again, let me just go and check. But then again, you can see that the linear trend is winning. Most of these errors is this one giving us the smallest error. Okay, so let's see here. So for the exponential smoothing, 8.5. Yes, you saw that 8.5. The adjusted exponential smoothing I didn't do, but when you check it, it will be slightly lower. The linear trend is 4.9. Okay, let me just show you in our own. I think it's the same approach, but there was a bit of decimal differences. So watch it. Instead of 4.9, instead of the 4.9, instead of the 4.9, we got 5.2 or 5.3. Okay. But I have the funny, interesting feeling that is because of the decimal differences somewhat. That is what is result. Let me just check this and be sure. I know why. Because that one is not supposed to be divided by 11. It's supposed to be divided by 12. So I think I divided it by 11. So let me divide it by 12. And then you divide this by that, you get the same thing. I'm going to do this. So that gives you 27. I didn't include the first one. That is it. So watch it. The sum here, you should have included all of them. I think I did not include the first one. So it's supposed to be here up to the end. Let me be sure. Because there's something that is sum of I20, I this divided by that. Then you have this one. We take this one divided by that. So why is it still showing 5.2? Anyway, you can check it. For some reason, okay, it is not exactly what it is in the document, but just double check to see why. But it's very close, and you can see that even if it is 4.9, it's still the leading one, as you can see here. It's 4.9, it's still the leading one here. Okay, so the linear trend seems to be winning all the errors because it's producing the lowest error. The next error is a mean squared error. Watch it. The mean squared error is the same as the MAPD. Okay, it's the same thing. You take the D minus the forecast. This time you square it and divide it by the sample size. You square it. You square each one. After you find the difference, you square. And I think I did that here. Okay. After you square it. This is the column here. Okay. So watch it. I squared each one. You sum it. And then you get 375.6, blah, blah, blah. Then you divide that by 11. Okay. Did I do? Yeah, this was the exponential smoothing. Divided by 11, you get 34.15. Okay, so let's see that here. That's at the far right, 34.15. Okay. Again, that one too, there's a slight difference. Do you realize that? Okay. There's some slight difference, which I think is so because we are using more decimals. They are not using more decimals. So instead of our 375.68, they had 376.04. So there's some slight difference there. Okay. So they used the 376.04 divided by the 11 and got 34.18. We had, what did we get? We had 34.15. It's almost the same. Okay, 34.15, they had 34.18. Okay, so ladies and gentlemen, this last one here, how was it calculated? It's just squaring the difference. You don't take the absolute value. You see, when you take the absolute value, it's one thing. It's one thing to negate the number. Another way to negate the number is take the square and then divide it by that. And then that will give you that's the mean squared error. The last one is the I think there's a last one, but I didn't do the last one because you don't need all of them. The last one is, let's look at that. Okay, this is the last one. The last one is a root mean squared error. Root mean squared error. Okay. So these are just the basics. And when you want to check whether a particular error is the best, the first three are enough. Okay, you would probably not even go beyond two of them. So that is how you use the errors to judge which method is the best. Is it a moving average? Is it a weighted moving average? Is it a simple exponential smoothing? Is it adjusted exponential smoothing? Is it the linear trend? Is it a seasonal adjustment? Okay, whichever one it is, that is what you use to be able to make a conclusion. Ladies and gentlemen, that brings us to the end of the entire caboodle. What a day, and what a time that this has been. Okay, at this stage, I'm going to wait for, in case you have a question, this is the time. Ask me as many questions as possible, and then we'll know what next to do.